Alright. Hey guys, welcome to our first lecture for SYSC 2003, and we're going a little bit of an intro to programming in HC12. So, first of all, we gotta look inside the processor. We're just gonna go right back to basics for now, and we're gonna look at the registers. So, registers allow you to hold data temporarily, and they can be transferred between memory and I/O. It's very basic but very essential stuff. So let's look at the 5 registers that come with this certain processor. So first one is the accumulators. All right. So the accumulators are made up of these D, A, and B registers. So the D register holds 16 bits, and it says here, I know it says 0 to 15, but that's because the first bit is named the 0 bit. So now the A and B registers are made up of 8 bits each. So if you want to store 16 bits into something, it gets stored into D. But if you're storing 8 bits, then A and B registers are your best friends. So the accumulators, they let you store data inside there, but so do the rest of the registers. But like you could store it. These are the ones that are used to store all the time. Like just use it. All right. So now we're gonna look at these X and Y registers. These are known as the index registers. We didn't really touch indexing in the lecture, so I'm not going to go over it right now, but we'll go over it in future lectures. Next, we're going to look at the SP and PC registers. So the SP is known as the stack pointer, and the stack pointer points to the top of a stack if we ever use a stack to store some data. So like that's what it's called and what it does, but we won't touch on it again for now, but we will later. So next is the program counter, and we use this program counter to look at which instruction you're at in memory. So all your instructions will be stored inside memory, and then your program counter points at which instruction you're at. And this is how your program is run. Each instruction is looked at incrementally, if that's a word. Alright, so next we gotta look at the flags register. So the flags register can tell you the state of a processor at any time. So we're just going to look at a few for now. So first one we're going to look at is the negative flag. That's not how you spell negative. Negative flag is also known as the sign flag, and it just tells you if your mathematical operation has returned a negative. Next is the 0 flag, which tells you if the mathematical operation has returned a 0. Your overflow flag tells you if your, again, mathematical operation has returned something out of its range. So if it returns more than it can possibly calculate, then it gives you an overflow. That's a problem usually. So, and the final one we're going to look at is the carry flag, which tells you if when you're adding stuff together, and after you've gone through all your numbers and you still have a carry flag left over, this carry flag gets activated, and it can be very useful to use in later in later things we'll do with in our time here, pretty much. So we'll look at the rest of the registers in another lecture as well. Alright, so next we're just going to talk a little bit about memory. So the memory is where you can store and all sorts of data, basically. You store instructions there, you store any kind of movement variables, any constants, anything essential to the processor running gets stored inside memory, and things can be read and written to memory as you wish, basically. So all the memory addresses inside memory are written inside hex, or in hex, and you'll have to reference them using hex numbers. So memory is split like it would be useful to say memory is split into different locations, so you will have different different addresses for each memory location. There are many different ways to access it in memory. We will cover like maybe one inside this lecture, but you will see all of them when we get through this course. Alright, so the next thing we're going to look at here is how to write instructions in HC12. So the first thing we have to look at is basically just how the syntax works. So first we look at the operand and the opcode. So the order that we will write instruction is first we write the opcode and then we'll write the operand like this. And basically what the opcode is just the operation that we're going to perform, and the operand is the address that is any addressing information we need. So a register, memory location, I/O port, stuff like that. That's what the operand basically states. So for the opcode, there's 3 different types of them. So one is a data transfer. So if you want to move something from memory to a register, if you want to move something from a register into a I/O port, say your computer screen, you would use a data transfer type for that. Data manipulation is basically just arithmetic. And finally, control flow is the order in which your instructions are basically read and stuff like that. Just how your program runs can be manipulated using code as well. So let's look at some examples of HC12 code. First of all, there's the LDAA instruction, which means it's the load instruction. All of these instructions are examples of loads. This load AA function, what it does is move something from memory into register A. This means that whatever is inside, so you have to specify what data you want to move, and you can move it straight into A. The same thing here for load AB. You will move whatever is in memory into register B. And then finally there's load D, which you move memory into register D. Next is the store function. What this does is move whatever is inside B, or whatever register you specify, and moves that out into memory. So there's store accumulator A, which will move whatever is inside A into the memory. And then there's store accumulator B, which is shown in this diagram here. It'll move whatever's inside B into memory. Okay, so now let's try writing some instructions in HC12. So first, let's look at the load accumulator A. And let's say we wanted to move the number 7. Number 7 is just an arbitrary piece of data. We're not getting it from any memory location. It's just from wherever, right? So to do that, we want to write the decimal number 7. So we're just going to write number here and the number 7. So now whatever is inside A, the number that's inside A is actually going to be the number 7 in hexadecimal, because anything stored inside memory or registers is always stored in hexadecimal. So this is a full 8-bit hexadecimal. Sorry, it's a full 4 bits of hexadecimal space, or of bit space taken up inside accumulator A. So now say we wanted to move into accumulator B the hexadecimal number 7. So to do this, we need to again write the number sign. but this time we have to write a dollar sign in front of the 7. So now inside accumulator B, we'll have 07. It does not have to convert it into hexadecimal before it stores it into 7 because you're just doing a hexadecimal number in the first place. Now let's say we want to move something from the memory location 7 into accumulator A. To do that we need to use, we don't need to put the number sign anymore, we just have to put a dollar sign and write 07. So now we'll look into memory location 0007, and it will take whatever's inside 7 and put it inside A. Now, let's say we wanted to store something from memory location 800 and store it inside A again. So let's load accumulator A, and from memory location 800, the same thing will happen. It will take whatever is inside 800 and store it in A. Okay? So these are different some examples of different instructions. So let's see here. Here we've immediately taken some piece of data and put it directly inside a register. This thing is accordingly called immediate addressing, because all you're doing is taking a piece of data and then storing it inside A. Same thing here, as it's also, you're just taking a piece of data, you're not taking it from a certain memory location. Over here, this is called direct memory addressing, because you're taking the memory location, you're stating specifically which one you want, and putting it inside accumulator A, so it's known as direct addressing. Now this is known as extended direct addressing. This is called that because 800 is actually a 16-bit number, because as you know, two digits in hexadecimal takes up 8 bits. So this means that since here we have actually 4 numbers, we're taking up the full 16 bits. Okay, so we have taken up a full 16-bit. We've given the instruction a 16-bit address. So this is what. So now this is the reason why it's an extended direct addressing mode. Now this stuff becomes important because we need to be able to convert this into machine code. So this allows us to view the written instruction here in assembly, and then we can translate that into machine code. Now, hold on 1 second, I will bring up a tool that will help us figure this out. Alright. Now here, you see I've brought up the documentation for the load A operation. So, right over here, we can see that right here references are the different types of addressing, and this is actually how we write out the machine code. So say we wanted to write out the machine code for the first instruction, load accumulator A and the number 7. We'd basically just write 86, and then since the number we wrote was 07 in hexadecimal, we just write 07. You've just written some machine code for load accumulator A. Congratulations. Now say we wanted to write the machine code for this line here, or the load accumulator A from memory address 800. So we know that it's extended memory addressing. So we have to write here B6, and then we write the memory address down. So first we have to write B6, and then first we take the high byte which is the 08 part, and then 00, because that's the rest of the address. And that's very easily how you write the machine code for different instructions. Now we know there's many different many more instructions that you can write, and you can find documentation just like this. I'd encourage you to read up on it and just learn how to read this documentation because it's very useful.